Okay, so figure 2 shows a picnic bench of mass 20 kg, which consists of a horizontal plank of wood of length 2 meters resting on 2 supports, each of which is 0.6 meters from the center of the plank. Luigi sits on the bench at its midpoint and his mother Maria sits on one end. Their masses are 40 kg and 75 kg respectively. By modelling the bench as a uniform rod and Luigi and Maria's particles, find the reaction at each of the 2 supports, so this support and this support. So first, for this question, you obviously need to use the information provided in the question. It says that the picnic has, or the bench has a mass of 20 kg, so you put 20g down, and you should always make sure that there's a g at the end when you're taking these masses. And it says that each of which is 0.6 meters from the center of the plank. So the distance from the center to each support is 0.6. And then you can say that the distance from one support to the end is 0.4, as obviously half of 2 meters is 1, and then 1 minus 0.6 is 0.4. So it says Luigi sits on the bench at its midpoint. So the midpoint would be somewhere here, so we can mark that as here and put 40g, which is his weight. And then Maria sits on one end, we can just say she sits on this end and mark that as 75g. And then we can draw the reactions at each of these supports. We can do this as R1 and this is R2. As the question says at each of the 2 supports, I guess we kind of can't assume that these are different. Obviously some questions might say that it's the same. Okay, so the first thing that you should know when you have a question like this, or even a diagram like this, is that the forces at the top are always equal to the ones at the bottom. So we have R1 plus R2, and that will equal 40g plus 20g plus 75g. So we can set that as our first equation. R1 plus R2 equals 135g, which is just the sum of these 3 masses here. And we can just call this A and this side B. And then we take the moments about A, so this will help us find the reactions. So if we take our moments about A using clockwise as positive, we can say 0.6 times 60g. These 2 added up, they're both in the centre, so this is 60g in total, times by the distance to get to A, which is 0.6, shown by here. So we know 0.6 times 60g is the first one. And then we can do plus 75g times by the distance to A. Our distance to A in this case is basically, we know this is 0.4, this is also 0.4, and the entire distance is 2. So we can do 2 minus 0.4, which gives 1.6. So this all the way to here is just 1.6. And then we can find our anti-clockwise moments. This is, so obviously we know that these ones are our clockwise ones. And our anti-clockwise one will be R2, which goes this way. So we do minus 1.2, which is the distance from here to here. We've got 0.6 plus 0.6, times by R2, we don't know what that is yet, and equals 0. And then if we multiply these out, we get this equation here, and we can just rearrange it like this. And then get R2 equals 130g. And then instead of doing the same thing for R1, we can just put this back into this equation from the top. So R1 plus 130g equals 135g, so R1 will equal 5g, and you get R1 equals 5g and R2 equals 130g. And obviously, most of the time in these questions, g will just equal 9.8, so you can also just multiply each one by 9.8. I think you can leave it either or, but I've just multiplied them by 9.8, so you get 49 newtons and 1,274 newtons. Part B. Luigi moves to sit closer to his mother. Find how close Luigi can get to his mother before the reaction at one of the supports becomes 0. So first, we know that as Luigi moves towards Maria, his mother, the bench will want to tip clockwise around the right support, so this one, which means the left support reaction R1 will start to decrease, and this limit is reached when R1 equals 0. So we're basically finding how close he can get to his mother before this happens. And we've got all of these which you set out from before. And we know that the distance from Maria to support B is 0.4. And the distance from the centre to support B is 0.6. Now say that Luigi here moved closer to his mother, like here for example. We can say that the distance from Luigi to support B equals x minus 0.4, and then we can take our moments about support B, and then we're basically solving to find x. So our moments about B, so we've got our anti-clockwise moments which equal our clockwise moments. So our anti-clockwise moments will be, so it will be 20g times by 0.6, and then 40g times by d. Obviously now that Luigi's not in the centre, it is just d. We don't know what d is. D is just the distance that Luigi is at. And then, yeah, d equals Luigi's distance. And then our clockwise moments, we can do 75g multiplied by 0.4. And then you can set these to equal each other to form this equation, as we know that our anti-clockwise moments will balance out with our clockwise moments. So we can rearrange it to get this, minus 12g. And then cancel out the g's, and we get 18 equals 40d. And then our d equals 18 over 40. And we get 0.45 meters equals d. So Luigi is 0.45 meters from support B before the reaction on the supports will become 0. So, for example, R1 equals 0. And then Maria is 0.4 meters from support B, because what we were doing was we were working out the distance from Luigi to support B, but we need to find out the distance between Luigi and his mother. So that will be 0.45 plus 0.4, and that gives you 0.85 meters. So Luigi can move 0.85 meters towards his mother. Okay, a beam AB has mass 12 kg and length 5 meters. It's held in equilibrium in a horizontal position by two vertical ropes attached to the beam. One rope is attached to A and the other to point C on the beam where BC equals 1 meter, as shown. The beam is modelled as a uniform rod and the ropes as light strings. So find the tension in rope C and in rope A. Okay, so what we need to do for this question is we need to obviously set everything out and lay everything out on the diagram. We're already told that the beam has a mass of 12 kg, so we can write 12g here, and it has a length of 5 meters. That's already drawn out here. It says that BC equals 1 meter, we've got that, and then we can just say that this equals S and this equals T. And then we can take our moments about A. And to do this, we obviously find the distance from A to the centre. That's just 2.5. And then we can do 12g times by 2.5. That is our clockwise moment. This is clockwise. Equals, and then the anti-clockwise moment, which is t times by 4. Because we know that 5 minus 1 is just 4. So it's going this way, anti-clockwise. And then just rearrange this equation. And you get t equals 7.5g. So that is t for this part, which is a tension in the rope C. And then again, we don't need to do all this really fancy stuff to find A. So we can just use the equation where we balance the top to the bottom. So we do S plus T equals 12g. We know that T is 7.5, so 12 minus 7.5 is just 4.5. So we know that S is 4.5, so the tension in the rope A is just 4.5. Okay, part B. So a small load of mass 16 kg attached to the beam at a point which is y meters, so we're not sure where this is, from A. The load is modelled as a particle. Given that the beam remains in equilibrium in a horizontal position, find in terms of y an expression for the tension in the rope at C. Okay, so we know that this is again 12g. And we know that we've got a mass now of 16g being added. We can put that here. We don't know where it is, but we'll just put it anywhere. And we've got our u, and we can put this as v. And then we can take our moments about A. So our moments about A, obviously in the anti-clockwise direction, are v times by 4. And then in the clockwise, we've got 16g times by y. We're not sure what the distance is, it just says y meters. Plus 12g times 2.5. Obviously, half of 5 is just 2.5. And then we've got this equation here, 4v equals 16gy plus 30g. We can simplify it further by getting rid of the 4. And that gives us v equals 4gy plus 7.5g. And that is your tension in C when obviously this is added. The rope at C will break if tension exceeds 98 newtons. The rope at A cannot break. Find the range of possible positions on the beam where the load can be attached without the rope at C breaking. Okay, so when v is less than or equal to 98, because this is when it exceeds it, and then we know that this equation is 4gy plus 7.5g, we can just put this value of v into this equation, and we get 4gy plus 7.5g is less than or equal to 9.8. We can multiply everything by 9.8. We know that g equals 9.8, so we can just do that and we get this. And then when we rearrange it, we get 39.2y is less than or equal to 24.5. And you get y is less than or equal to 5/8. So that is the range of possible positions. The load must be no more than 5/8 meters from A, basically. A beam AB has a length 4 meters and a mass 20 kg. The beam is suspended horizontally by 2 vertical ropes. One rope is attached to the beam at C, where AC equals 0.5 meters. The other rope is attached to the beam at D, where DB equals 0.7 meters. The beam is modelled as a non-uniform rod and the ropes as light inextensible strings. The beam is modelled as a non-uniform rod and the ropes as light and extensible strings. It's given that the tension in the rope at C is 3 times the tension in the rope at D. Determine the distance from the centre of the mass from A. Okay, so we're going to look at what this question has given us. It's saying that it has a length of 4 meters, which is given here, and a mass of 20 kg. So we can just put 20g down here. Blah, blah, blah. AC is equal to 0.5. You've got that. DB is equal to 0.7. And then you can just put these C and D. So we've got tension C and tension D as our sort of reactions. And then now we can just find the moments about A. So moments about A here, we've got anti-clockwise moments being TC and TD. So TC times 0.5 plus 3.3 times TD. We know it's 3.3 as a distance from D to A, as it's just 4 minus 0.7. And then we can work out our clockwise moments, which is only 20g, so going this way. We've got 20g times by x because we're trying to find the distance of the centre of mass from A. So we're not sure what this distance is. It's not 2, as the question hasn't said anything about that. It's asking us to find the actual length. So then we can rearrange this equation and set the anti-clockwise moments equal to the clockwise moments. So you get something like this. And then with vertical equilibrium, you know that these upwards forces are going to equal the downwards. So we'll do TC plus TD equals 20G. And then obviously the question has told us that the tension in the rope at C is 3 times the tension in the rope at D. So obviously C is 3 times D, so you can just do 3D is equal to C. So you can do 3 TD plus TD equals 20G, which gives you 4TD. And then you can write TD is equal to 5. And we can use this equation, and 5 TC plus 5G equals 20G, TC will equal 15G, and then you can put this back into this equation here, and then we can just add everything up. We get 24G equals 20Gx, we can get rid of the G's, and then we can divide on both sides by 20 to get X on its own, and that will give you 1.2 meters. Okay. A particle of mass mkg is now placed on the beam at a point where the magnitude of the moment of the particle's weight of about C is 3.5 mg Newton meters. The beam remains horizontal and in equilibrium. Determine the largest possible value of m. Okay, so the first thing that we need to do is obviously use this equation, which is moment equals force times distance, and we just need to find the distance of m. So we know that our moment is given as 3.5 mg, and that will equal mg, which is your force, times by distance. If you cancel these two out, you get 3.5 equals d. So this is our distance. Now, since C is 0.5 meters from A, and it's saying that this distance here is 3.5 meters away from C, then you can say that 0.5 plus 3.5 equals 4 meters, which basically means that if it's 4 meters, it's at the very end of B. So for the highest value of m, the beam is on the tipping point, so the tension at C will be 0. So this will be 0, as obviously if this is at the end, and we need to find the highest value, then this will be on the point of tipping, and this will just be 0. Okay, and then obviously we've just got this going at the end here, and we can take our moments about D. So we know that it's 0.7 times by mg, and then from 20g we multiply it by 2.1, which is the distance here. We know that the distance from the centre of mass to A is 1.2, and then the distance from A to D is 3.3. You do 3.3 minus 1.2, and that gives you 2.1. So basically this is 3.3, and then this is minus 2.1, and then you just get this distance. So 20g times by 2.1, and then you equal to each other. And that gives you 0.7 mg equals to 42g. Cancel out the g's, multiply everything by 10 and divide by 7, and you get m equals 60. Okay. A beam AB is supported by two vertical ropes which are attached to the beam at points P and points Q, where AP equals 0.3 and BQ equals 0.3. The beam is modelled as a uniform rod of length 2 meters and mass 20 kg. The ropes are modelled as light inextensible strings. A gymnast of mass 50 kg hangs on the beam here between P and Q. The gymnast is modelled as a particle attached to the beam at point X, where Px equals x meters between this range, as shown in figure 2. The beam rests in equilibrium in a horizontal position. Show that the tension in the rope attached to the beam at P is 588 minus 350x newtons. Okay, so that's really quick, but yeah, okay, so it's asking us to find the tension in the rope at P. So this entire distance is given by 2 meters, so that's 2 meters, and then obviously the mass of this beam is 20 kg, so we write 20g, and the mass of the gymnast is 50 kg, so we write 50g. And then this will be our TP, and then we'll take our moments about Q to find this. So our moments about Q, well, we've got clockwise moments, which will be this way, and that will give you TP times by 1.4. How do we know this? Well, from A to P it's 0.3, same with this, so 2 minus 0.3 minus 0.3 will just give you 1.4 in the middle. So 1.4 times by TP, so 1.4 times by TP, and then for the anti-clockwise, you've got 50g times by 1.4 minus x. So this is entire 1.4, and this is minus x, because we obviously don't know what this distance is. And then plus 20g times by 0.7. We know that obviously this is in the middle here, which is at 1, and then obviously 1 minus 0.3 is 0.7. And then we can set our equation. We can equate the clockwise moments to the anti-clockwise moments, and you get this. And then we can expand this, and we get 1.4 TP equals 70g minus 50gx plus 14g. And you get this. And then we multiply everything by g. And we know that g is 9.8, so you'll get something roughly like this, as obviously the form of the p is not in g, so we need to multiply that out. And then divide everything by 1.4, and you get TP equals 588 minus 350x. Find in terms of x the tension in the rope attached to the beam at Q. So it needs to find this tension now, and it's in terms of x, like the last tension of P. This is just what we know from earlier. And then we know that TP plus TQ equals 20g plus 50g. We obviously know that the upwards forces will equal the downwards ones, so 50g plus 20g will equal TP plus TQ. And that's TQ here. And then that will roughly equal 686, or not roughly, I think actually does equal 686. And then we know that TP equals 588 minus 350x. You can put this back into this equation here, so this into here, like this, and then we can rearrange it. We can add the 350x to this side, and then we can minus the 588 on both sides. You get TQ equals 98 plus 350x. Given that the tension in the rope attached at Q is 3 times the tension in the rope attached at P, find the value of x. So obviously from before, we know that TP equals 588 minus 350x, and TQ equals 98 plus 350x. We know that TQ is 3 times TP, is given in this question here. So at Q is 3 times the tension in P. And then we can put these in, so we can do obviously this TQ equals 3 times this. And then we can expand that, and we get something like this. And we can add the 150x, and then you can minus 98, and you get something like this. And then you can just divide everything by x, and you'll get x equals 1.19.